Okay, so we can start now. So we are very happy to have here Arkajyoti Manna from IMSC. And he's going to tell us about new recursion relations for scattering amplitudes with massive particles. Over to you, Arkajyoti.
Thank you so much, sir. Hello, everyone. Today, so first of all, I want to thank the organizers for Quantum Space-Time Seminar Series for giving me the opportunity to present our work here. The title of my talk will be the new recursion relations for scattering amplitudes with massive particles. This is based on this paper, which is done in collaboration with my colleague Saurabh Vallabh, who is also from IMSC. Okay, so let me start this talk by asking the following question: why should we need an alternative approach to compute scattering amplitude other than the usual field theory techniques? So there are several reasons, but let me focus on the following example. So let us consider a tree-level endpoint gluon amplitude. This is completely determined by only 3-point vertex. So we would be interested in the trivalent tree graphs with n external legs. So as you see that for n equal to 4, there are 2 diagrams, but when we go to from n equal to 4 to n equal to 5, there are total 5 diagrams. So this number will increase rapidly as we increase the number of external particles. The number of trivalent diagrams are roughly given by these scattering numbers. So in this table, I have listed the number of diagrams and the number of total diagrams to compute the full amplitude. So remember, these amplitudes are only color ordered. The full amplitude can be constructed from these diagrams with using the well-known color decomposition. So I want to make 2 remarks on this, that the number of diagrams grows rapidly with n, and each diagram corresponds to an increasingly complicated expression that we get from QFT calculation. So let us look at the result. If we look at the result, the amplitude for n external gluons with 2 gluons with helicity -1 and rest have +1 helicity, then the result is just this single simple expression. So this tells us that there might be some efficient ways to calculate the scattering amplitude. So the surprising simplicity and enticing mathematical structure, along with the practical relevance for particle physics, motivates the current studies of scattering amplitude. So the current studies of scattering amplitude, as the idea that's central to these studies, are called on-cell method. So usual perturbative QFT, or the Feynman diagram way to calculate scattering amplitude, involves enormous amount of unphysical degrees of freedom, which is called gauge redundancies that we all know. So in the on-cell methods, what happens that we have to directly deal with the particles instead of any quantum fields. So we don't have any attendant gauge redundancy that comes with these quantum fields. For example, Brito, Kachajo, Feng, Witten recursion relations and generalized unitarity for this on-cell method. So what about the massive particles? For massive particles, as we know, there are no gauge redundancies. So these advantages seems to cease for the massive particles. But we will see.
One question: What do you mean by generalized unitarity as opposed to just unitarity?
Generalized unitarity means. So in what happens in the calculation of loop amplitude, we use split the loop amplitude in terms of tree-level amplitude, and the tree amplitude are computed via the unitarity. So it's not that we are using unitarity directly to compute the loop amplitude, but we compute the tree-level amplitude, which is used to compute this loop level amplitude. It's not directly using unitarity in computation.
But in the reduction of the loop amplitude to the tree level amplitude, this is by Katkowski's rule, right?
Right.
So that's a statement of unitarity, though, right?
Yeah. Yeah, I'm not sure.
Maybe, sorry, can I just make a small comment?
Yeah.
Please.
Yeah, so the generalized unitarity of it is beyond Katkowski rule. So the idea is that in usual unitarity we do one cut. But in generalized unitarity we can there are techniques where you do multiple cuts which have no connection directly with unitarity at all, and still can be used to compute the loop amplitudes. So basically, for example, in a square box you can do 4 cuts, and this you cannot understand in terms of unitarity, and this is called generalized unitarity.
Okay, but and then I mean, unitarity is what makes Katkowski's rules true, right? So
Correct.
this prescription, the new prescription that you're giving me, what makes that true?
Yeah, so that is precisely because you in the generalized unitarity, the reason it works is because you think of Katkowski rule, but you apply it to complexified loop momenta. So it kind of get generalized where you basically deform your loop momenta to complex space, and there you can see that you can consistently solve for, you can put like say 4 propagators in a box on shell consistently if your loop momenta is allowed to be complex. So this is very much tied to allowing complex deformations of your momenta.
I see. And unitarity, one can mathematically show that whatever unitarity would mean on the real locus continues. You just continue that statement to complex.
Exactly.
I see. Values. Okay. Thank you.
Okay, so the motivation for this work is the following. So in this talk, we'll be focusing on BCFW recursion scheme and its generalization to the amplitude, including massive particles. So the ingredient we need to compute the amplitude in BCFW method is the on-cell 3-point amplitude. The advantage over the Feynman diagram calculation and unitarity methods are as follows. The Feynman diagram calculation is not recursive, and unitarity method, we cannot use the on-cell 3-point amplitude because the 3-point amplitude will vanish for real momenta in the Minkowski signature. So in this method, we need to consider only a few number of diagrams that we will see in a next few couple of slides. This method proves to be efficient to compute both tree and loop level amplitudes. BCFW recursion for massless particle is well known due to this work. The work of Arkani-Hamed and Huang on massive spinor-helicity formalism is force space-time dimensions has unified the kinematic space of massive and massless particle into spinor-helicity basis. So in light of this discovery, it is natural to ask if one can complexify the massive external leg to obtain a recursion scheme similar to BCFW. So the outcome of this our work is the proposal for a generalization of BCFW recursion scheme to the case when one massive and one massless momenta get complexified. So the plan of my talk will be the following. So I'll review the BCFW recursion scheme for both massive and massless amplitude. Then I'll review the massless and massive spinor-helicity formalism following this reference. Then I'll propose the a little to covariant massive massless shift, and I'll give an example of how to compute a 4-point amplitude using this shift. Then I'll try to prove the validity of this shift by first reviewing the valid shift in massless amplitudes, in particular for gluon amplitudes, and then I'll talk about the proof of massive massless shift in Higgsed theory. So let me first give you the outline of BCFW recursion scheme. Consider an n particle tree level amplitude as a function of real momenta. Pick any 2 external momenta pi, pj, and analytically continue to that complex plane while keeping them on cell and maintaining momentum. In particular, we'll take pi, we'll deform pi like this and pj like this, where the shift vector q mu obeys the following conditions to maintain the momentum conservation and on cell condition for this deformed momentum. The amplitude is now a meromorphic function of z, and the original amplitude, which is a function of only real momenta, can be recovered by a contour integral around the origin. So under the assumption that z equal to 0 is an isolated singularity, the contour of integration can be extended to infinity to give this. So here we have residue of this object at finite z, z equal to zi, and there is a residue at z equal to infinity. So we'll see that the recursion to work, this residue at infinity have two values. So the tree amplitude have complete extremely simple analytic structure. It has only simple poles in kinematic space coming from the propagator. So the on-cell property of the shifted propagator yields finite poles in Z-plane by writing the on-cell deformed propagator like this. So there is a simple pole in the Z-plane where this Zi can be determined like this. Furthermore, the residue at Z equal to Zi can be interpreted as a product of lower point amplitudes like this. So the first term corresponds to the case when the exchange particle is massive with mass m, and the second term corresponds to those diagrams where the exchange particle itself is massless. So the index ij includes all possible helicity of the exchange particle as well as the scattering channels. So assuming that,
Sorry, 1 second. So I thought if the propagator is that of a massive particle, then you should just get the first term, right? Why are we getting the second term as if there is some massless particle being exchanged?
yeah, so for some cases like this, so let me give you this diagram. So there is n particle amplitude where both massless and massive particles are involved. So, but there may be some diagrams where massless particles are exchanged and massive particles are exchanged. Right?
Oh, okay. So you have what you are doing is you are working in a theory with one massless particle and one massive particle, or a bunch of massive particles, bunch of massless particles, all of which are allowed to be exchanged by symmetries,
Yes,
and
yes.
then you just write
Right,
down
right.
the equations. Okay.
Right.
Fine.
So I'm allowing all kind of exchange. Yeah.
Okay.
So assuming that residue descriptor vanishes at large z equal to infinity.
Internal particles are massive or massless?
Yeah, if I am allowing internal particles to be both massive and massless at this moment.
And the external ones?
External ones can also be massive and massless. So in our proposal, we only need one massive and one massless particle to be in the amplitude, because we'll talk about massless and massive shift, but all the other particles can be either massive or massless.
Okay, thanks.
Okay.
And your IJ are labeling just the
the all possible.
Oh, okay, helicities. Okay, fine. Mm-hmm. Okay, yes, thank you.
So at large Z, if the residue vanishes, then the BCFW recursion scheme can be given like this. So here the sub-amplitude are on cell.
Sorry, 1 second. Can you go to previous? Here, let's see. You're saying I corresponds to helicities, and why does your P also have a subscript I?
Oh, so for example, like if you consider a diagram like this, so here the exchange particle is massless, right? So there are so if this left sub amplitude have some, suppose two legs are attached, then pi will be p1 plus, I mean the sum of those two momenta. But if the left sub amplitude has three momenta suppose attached, then your pi will be changing, right? Sum of all three momenta. So that I will also indicate the scattering channel. I mean,
okay.
So diagrammatically, the recursion scheme can be realized as follows. So here the wavy lines are massless particles and solid lines are massive. So only diagrams in which the two deformed momenta are on opposite side of the on-cell propagator contribute to the residue at z equal to 0. So we will see that this will enormously simplify our calculation in practice. We will see in an explicit example. Okay. So let me make some comments about the vanishing of the deformed amplitude at large Z. So BCFW recursion scheme works when the boundary term R vanishes. Alternatively, the complex shift is called valid when the scriptor vanishes. Usually, this can be achieved by demanding that the amplitude itself is vanishing at large Z. But this demand is far from obvious and not even true in any general theory. For example, if you look at any generic Feynman diagram, so for the gauge theory or gravity, for gauge theory, suppose these legs are all deformed. So for because in gauge theory there is a single derivative acting on the field, all the vertex will scale with order z, and the propagators will scale with 1 over z. So in that case, at large z, the amplitude will diverge at z, like z, and for gravity, it is much worse, as you can. So, but there are certain amplitudes in gauge theory and gravity with specific Higgsed configuration which vanish at large z. We'll see that due to the emergence of an enhanced spin symmetry at large z, together with the word identity, restricts the behavior of on-cell amplitude as an expansion in 1 over z at large as z is going to increase. So the boundary term are for massless theories like scalar Yang-Mills, scalar graviton do not have any BCFW recursion equation. For these theories, the amplitude do not vanish for any Higgsed configurations. But for massless Yang-Mills theory, linearized gravity, the amplitude and large z vanish. Hence, the BCFW recursion works for these theories. So scalar theories do not enjoy any enhanced spin symmetry or any other constraints like word identity, like the theory, gauge theories and gravity does. So there is no BCFW recursion for those theories. But in certain cases, one can extend the domain of BCFW recursion to include scalar theories. For example, consider the lambda 5 theory. Given a 4-point amplitude A4 equal to lambda, it is possible to compute higher point amplitude starting from A6. But with this data also, the on-cell recursion fails to produce the correct amplitude. This precisely happens due to the non-vanishing boundary term at large z. And it also turns out that the boundary contributions comes from those diagrams where two shifted momenta are attached to the same subamplitude. So in these diagrams, one can recursively compute the amplitude. So one can be able to recursively compute the boundary term and therefore the full amplitude. So is there any question? If not, let me move on to the review of spinor-helicity formalism for massless particles. For massless particles, the
can you express this condition that the part at infinity should vanish in a succinct way? What was the condition?
So there is no specific condition, but we'll see that for some specific theories like gluons and gravity, there are some with some specific external helicity configuration. There is an enhanced spin symmetry at large z that emerge at large z, and the word identity will restrict the behavior of this quantity at large z as in expansion in 1 over z. So there is no,
Sorry, go ahead.
Yeah, so I'm saying there is no specific condition for this to be 0. At least, I mean, in a naive way, it will always diverge for any general theory.
But is this what is called a Rege limit or something? I mean, well, okay, in the 4-point case. So in other words, first of all, if does this condition need to be checked for all n, or if it is true for, let's say, n equals 4, it will be true for n equals 5 and so on, or for every n this is an independent condition?
The theories that I will talk about, we need to check only for the n equal to which is the propagator. see that from that we can see that the 3-point amplitude also vanishes. But if the 3-point amplitude vanishes, in the recursion, one can construct any n-point amplitude from that 3-point amplitude. So any n-point will also vanish. But this is not true for any general.
So yeah, so suppose does this vanishing depend on the number of derivatives in the interaction, like which generate the vertices?
Yes, of course, but so that will give you the how the vertex will scale. But in general, in a naive analysis, it will anyway diverge at large, right? Because the interaction in a gauge theory, there is interaction with derivative terms, right?
Right.
It will, and for scalar theory, it will diverge like order z to the power 0. So.
But like a naive divergence of a, say, an interaction, an from an interaction term, I cannot say that, like, I mean, therefore, like, I can't use this recursion relation. Is that some? Okay.
Right.
Okay. I see.
Sorry, Arka, just to clarify, this is a property of the full amplitude, right? It is not a property of some individual Feynman diagram.
No. It's not a property of a full individual. Individual Feynman diagram. So it may happen that one Feynman diagram has some order z, but there are instances that you have some Feynman diagrams with order some function of z, which is exactly cancelling that term. Then your full amplitude has a good behavior at large. Vanishing behavior at large.
And just to sorry, Arka, just one more comment about Abhijit's earlier question that about the all n that he asked. So if you have, like, say, for example, scalar field theory with phi cube plus 5 to the 10 coupling, then up to 9 point it will suffice to just check it for. If you have checked it for 4 point, then it will give you.
Right.
But if you have contact term coming at 10th, then it will break down. So.
Right.
So really, gauge invariance plays an important role where lower point couplings determine all the higher.
Yeah. Okay, thank you. So, okay, but just at the kinematical level, if you look at the 4-point function as a function of Mandelstam variables, what sort of limit does z equal to infinity explore in the Mandelstam space? Which points do correspond to z equal to infinity? I guess that depends on which momenta you are trying to deform and so on. But let's say I do it in all possible ways and reach all possible points in the Mandelstam space. What are those points?
Arka, maybe you won't. Sorry, you can say it.
Yes, so actually, at infinite momenta, it will be like an iconal limit, right?
It's an iconal limit.
Which is what in the Mandelstam space?
Suppose Rachel.
Is it first of all complex SNT? You have to go to complex SNT and then what? Which directions?
The will be complex.
Are they correlated or just s equal to infinity, t equal to infinity? Just probably not, right? Because I guess you still have to obey momentum conservation and Marshall conditions. So
yeah, that is always obeyed. But maybe one way to understand it is that if the large z limit, basically this gives you just a scattering of one particle which is propagating in the background of a heavy fields which are not fluctuating at all. So the one that you are deforming only two momenta.
Okay.
So so in the z going to infinity limit, like you can think that the other particles are not fluctuating at all. So they just give you a background and you have a particle which is just propagating and scattering in that.
I see. So that is just trying to figure out what it means for the Mandelstam variables.
Yeah.
Sorry, Mandelstam means that depends on which one you are deforming. In general.
Well, you pick anything. You pick any call anything SNT, and then what happens?
But is it some largest fixed kind of?
Well, I mean, yeah, I mean, so if you so that if you take two momenta which are say in a 4-point scattering, say you're deforming say P1 and P2, for example, then your I think in the I mean, Arka can say more, but maybe then the U channel will dominate. I mean, will come as the because you're yeah.
Okay. Yes. Thank you.
And just to ask again, like I can't use this as a sort of a constraint, right, on what possible ANs can give rise to a legitimate amplitude, right? That because you said that there could be ways in which this thing decays. I'm not carefully doing the deformation, basically. Is that correct?
Yeah. So that's true because so when I say that there are theories when the BCFW recursion do not work, this is also you have to careful about which external legs you are deforming. So theories like this, the scalar Yang-Mills and scalar graviton, when both the scalars legs are deformed, then you do not have any BCFW recursion. But suppose you deform the one gluon and one scalar leg, then we'll show in the later part of the talk that we'll show that there is a BCFW recursion scheme. Is that answer your question?
So to rule out any possible theories, one has to look at all the possible deformations that you perhaps can make, like, and in order to say that truly there is no BCFW recursion.
Recursion, yes. But for gauge theories and gravity, I can say that if you have checked the amplitude with specific with specific helicity configuration for which the larger amplitude is vanishing, then it will work.
Sorry, but that the recursion relation should be obeyed is not a fundamental condition on IMSC, right? Is it?
No, you have, so this recursion relation is, so I am saying that assuming you have this relation, the last one, because if you have any contact time, like Alok said, like phi 10, right? So then this recursion relation will not work, right? For contact time, this.
Right. And it's not like there is no underlying fundamental condition which says that, because why I'm asking this is because that, because there are some fundamental conditions that scattering amplitude needs to obey, right? Like a Froissart bound and so on. So the existence of recursion relation does not follow from any of those, right?
Yeah.
No, it does not. No.
So it's just a luxury that you may have in dealing with amplitudes. Is this true?
Right. For particular.
Okay.
I mean, generically in theories with gauge invariance, it seems like you do have.
Okay. I see.
No,
but Alok, why do you say that? Because I mean, you could write down, very high derivative terms in photonic theories. Just a bunch of derivatives on f. Keep all the gauge invariance, but write down a very high derivative term, and then presumably this is not going to be valid, right? Or would it be?
Yeah, I mean, that's not completely obvious. I mean, there have been theories with higher derivative terms like f squared terms, and they are still BCFW constructible. I mean, there's no proof like that. If you just add, you destroy the constructibility of, because there may be cancellations even with higher derivative interaction at large Z. The question is that individual diagrams will not decay, but when you sum, what happens? So it's not a priori obvious that if you just add higher derivative terms, you do not get a BCFW constructibility.
As you are saying, you may be able to find a particular locus in the phase space where this is obeyed.
Yes.
Particular complex plane in the complexified, let's say, phase space in which this is obeyed. Is that?
Yes, exactly.
Even though high derivatives may exist.
Yes.
How do you make present? I see. Okay, thank you.
Okay, so,
yeah, sorry, Arkajyoti, please go ahead. Yeah.
So let me review the spinor-helicity formalism of massless particles. For massless particle, the determinant of the momentum vector expressed in SL2C indices is 0. So therefore, the rank is 1. And then, so we can express this matrix in terms of a direct product of two component vectors, lambda and lambda tilde. So lambda and lambda tilde are called massless spinor-helicity variables. So the little group scaling for these variables are like this. But T is a non-zero complex number, and so the useful notations are this angle bracket and square bracket. These guys will appear in the expression of the amplitude. So the definition of this angle bracket and square bracket are as follows. And we will also want the reality condition of on this momentum. So that will tell us that the lambda and lambda tilde are related like this in Minkowski signature spacetime. So transformation of the amplitude under the little group will be like this. So if lambda scales with t and lambda tilde scales with t inverse, the amplitude will go like e to the power minus 2h, where h is the helicity of the massless particle. Okay. So let me talk about the 3-point massless amplitude, which is a basic building block of any recursively expressed amplitude. So if you look at the 3-point, the kind of kinematics of 3 particles, then you see that then we'll get the this condition. This condition tells us that the 3-point massless amplitude can be expressed either in terms of this angle bracket or the square bracket. So using the little group transformation like this, one can completely fix the structure of 3-point amplitude up to the coupling constant G and G prime. So the constants on the sum of the helicity ensures that the amplitude has a smooth vanishing limit for real momenta in Minkowski signature, because for real momenta in Minkowski signature, if you have vanishing, suppose angle bracket, then because of the reality condition, then the square bracket is also vanishing. So in this case, the 3-point amplitude will vanish. But this vanishing will have a smooth limit when we put the extra conditions on the sum of helicity. So there are two common remarks, that all positive helicity and all negative helicity 3-point gluon amplitude will vanish, and the amplitude vanishes when the sum of all the 3 helicities is 0, except for the case of the scalars. Okay, so let me give an example of 4-point massless amplitude.
Sorry, this a plus is 0. That follows from this expression, or?
Yeah, so it follows from the expression, but in that expression, when you have this configuration, then the G. Yeah, so the if you look at the corresponding Lagrangian interaction, it will be like non-local. Is that question?
No, I was just trying to see if this follows from this what you wrote down, or is something that.
It is a.
Yeah, sorry for this. This is very basic, I guess. Yeah.
No, you're right. It is not. So from this you get a finite answer. But what I'm saying that if you take that amplitude and try to look for the interaction for which this amplitude gives rise to, that interaction will be non-local.
Okay.
Because yeah.
Sorry, because what?
Yeah. So I'm saying that, for example, like plus, right? So you have to use the first expression.
Yeah.
So right. So it will be a product of 1 to all the 3 brackets, and the corresponding Lagrangian interaction. What happens that the derivative, the box operator will be in inverse position. So the theory will be non-local for that.
Okay.
So it's the same case happening with the second remark also.
Mm-hmm.
Is that okay?
Yeah. Go ahead. Yeah.
Okay. Okay, so let me give you an example of a 4-particle massless amplitude where we are considering a 4-gluon amplitude with these helicity configurations. So we are considering only color ordered amplitude. So there will be a single diagram due to this shift. So in the usual unitary method, there will be 2 diagrams, color ordered diagrams. But the as we are considering adjacent shift in 2 and 3, that only single diagram survives, because in the other diagram 2 and 3 are attached to the same vertex. So that will not contribute to the BCFW. So we'll use the, in particular, we'll use the BCFW shift 3-2, and 3 and 2, the spinors are deformed like this. And you can find the JDI from the on-cell condition on the deformed momenta. And using the Recursion relation, one can easily find the answer for this 4-particle amplitude like this. Okay, so let me
Sorry,
tell
this
you
was
about
in
the
one channel, right?
No, it contains all the channels, because so we are considering only color ordered diagram. So there will be 2 channels only. So 1, 2, 3, 4 and 1, 4, 2, 3, right? But the second diagram has the 2, 3 attached to the same vertex. So that will not contribute to this.
Sorry, no, I mean, what do I mean? I mean,
Oh, you are saying the
if you
helicity
don't have, let's say, gluons and stuff, just scalars. If I want to do this just with scalars, then if I were to take only one such term, then there's just one channel, right? I have to sum over all such decompositions, don't I?
Yes, but in that case, so you are talking about, if you are talking about phi q, then in that case the BCFW recursion itself not work, because the boundary term at infinity is not work.
Okay. I don't know if it is just me, or if everyone is having a little bit difficult time hearing Arkajyoti.
Hello,
Maybe
can you
just
hear
me.
me?
Yeah, I can.
Yeah.
I can hear him clearly.
Yeah, sometimes I'm getting cut off, but it might be my internet problem.
Okay. Fine.
Is it okay now?
It's better. Yeah.
Yeah.
Okay.
Okay, go ahead.
Yes. Yeah. So at the beginning of the talk, I told you about the endpoint MHV amplitude, which is also called particular amplitude, and I say that the new techniques may help us to calculate this amplitude efficiently. So let me try to sketch how to compute this for any endpoint amplitude. So for consider an endpoint MHV amplitude with 2 adjacent gluons having negative helicity and the rest of them having positive helicity. So there will be again 2 diagrams. The diagrams with single gluon having negative helicity and rest of positive helicity vanishes except for n equal to 3. So for this amplitude to compute, we will deform the external momenta like this. So for this gluon, for the Young's theory, the valid shifts are like this: minus, 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 plus, and plus, plus. The other possible shift plus minus is not valid for this theory. So we'll use one of these 3 shifts. So let us use 1, 2 shift. So in this case, we are using minus shift. So we deformed 1, 2 like this. So due to this particular shift, the contribution from the first diagram, this diagram, vanishes due to the vanishing of this 3-point amplitude. So only the second diagram will contribute to the amplitude. So as this is an inductive tube, we'll assume that this left sub-amplitude has the form of a particular amplitude, and we'll use that in the recursive relation to show that the n-point amplitude has the same form with an additional external gluon. So that leads to the this expression. So at this point, let me point out that the two-line shift that we are discussing, just discussed right now, are not special in any sense. One can perform multi-line shift as well. Usually, this leads to simplification in the calculation. For example, one can do all-line shift to compute amplitude in 5/4 theory, where the boundary term itself will decay as 1 over z at large z. So we don't have to compute the boundary term. A single recursion will be enough to compute the amplitude in this theory. Is there any question? So, but also, let me tell you that the simplicity involving this BCFW recursion comes at a cost. Although the BCFW recursion is very extremely powerful tool to compute amplitudes efficiently, it does not manifest a key feature of the underlying physical theory, which is locality. Let me demonstrate this point by considering the following 6-point NMHV amplitude, where gluons have these particular helicity configuration. Again, there will be two diagrams, two possible color order diagrams. For these two diagrams, we get these results. Now look at any of the result. The denominator has this kind of term. So this term will vanish when the action of P1 on the spinor 5 is exactly cancelled with the action of P6 on spinor 2. So this is a simple pole, but this doesn't correspond to any propagator. But at tree level, locality tells us that simple pole will come from only propagators. So this is simple pole is an unphysical pole, which is also called spurious pole. But it can be shown that the sum of these two terms has no spurious poles. So this is shown in this paper, but due to the complicated procedure, I will not go to the. I just want to mention that this BCFW recursion does not manifest the locality of the underlying physical. Okay, so let me end the review of massless amplitude here, and I'll now review the spinor-helicity formalism for massive particles following this. So for the massive particle, the determinant of P is not 0. So hence the rank is 2. So any rank 2 object can be expressed in terms of a combination of rank 1 object. So if so this sum is over this object, but for individual I, this object is a rank 1 object. So yeah, so okay, so we will associate this I index to the little group of the massive particle, which is actually the SU2. The little group transformation for this massive spinor-helicity variables are like this, where the W's are SU2 matrices. So for expressing the massive amplitude, there will be objects like this, angle and squares. So the angle bracket is defined like this, and square bracket is defined like this. It's similar to the massless case also, but it has this additional IJ index which corresponds to the little group of the massive.
Sorry, I didn't quite understand this point about spurious poles. So when you, I mean, if you don't use this spinor-helicity notation, etc., just the ordinary momenta, then the way you presented the BCFW relation, it was the factorization of the tree amplitude into two tree amplitudes joined together by physical poles, right? The poles corresponding to the exchange particle. So
right. But
in that way, it's manifestly local because you are seeing everywhere that that a particular particle is being exchanged.
Right.
Is it an artifact of this spinor-helicity or what? Yeah, go ahead.
So it is an artifact of the spinor-helicity variables, but the point is that in the BCFW case, we didn't actually use that the unitarity and locality to get the recursion. We say that the amplitude has a simple analytic structure, that it has this simple pole. So
Yeah,
you can see that from the
in the line below, for example, you are writing n point amplitude as a factorized form with the which is glued together just by an exchange, the pole corresponding to exchange, which I would call a physical pole. So in that sense, all the poles you are getting on the right hand side are physical ones, right? So
yeah, right. So in this expression, you can say this pole is actually physical, but when you write the amplitude in terms of the spinor-helicity, so you have to express your deformed momenta like this, right? Deformed,
okay,
sorry,
so
spinor.
it's the loss of locality is not due to BCFW recursion relation. It's due to the usage of these variables. Is that the case? Loss of manifest locality, let's say.
No. It is
No.
because of BCFW. So
because the values v at which the poles happen are unphysical from a physical point.
Yes. The spurious poles are most clearly manifested in spinor-helicity, but they will be there even if you just used.
No, but the prescription is to write down poles of an exchange particle there, right?
But the exchange particle has a deformed momentum. So the point is that that in if you look at the individual diagrams in BCFW, then the particle which is going on shell is not the real particle. It's what is going on shell is a complexified momentum, the p hat, what he's calling. So that gives rise to some locations in the in the complex Z plane, which are not always corresponding to physical poles. But of course, in the end, you do not they add up to 0, which is the main thing. So this, it is only in the intermediate steps that we see these spurious poles, which are there in some individual terms. When you add them, in the end, there is no spurious pole. You get the right amplitude.
Okay.
Yeah, and that's because you are not using local description to evaluate this. This amplitude.
Okay, I have to think about this. It's not immediately clear, but thanks. Go ahead, yeah.
Okay, yeah. So now we want to compute a massive amplitude. So the goal is to construct the massive amplitude in a little group covariant way. So in that case, we will use the symmetric 2s representation of SU2 group, because in the if we use the usual 2s plus 1 representation of SU2, then it will demands that we have to choose a particular direction. So that will break the rotational invariance of the amplitude. So we'll use the symmetric 2s representation of this SU2 group. So the desired little group covariant transformation is like this, but W's are again SU2 matrices and T is a non-zero complex number. So unlike the massless case, now the spinor-helicity variables lambda and lambda tilde are related via this Dirac equation. So in an expression of amplitude, which is now a function of lambda and lambda tilde, one can use these relations to express the amplitude in terms of purely in terms of lambda or lambda tilde. So here what we have done is that we express the amplitude in terms of lambda variables, and there's a part of the amplitude which is has this SL2C Lorentz index, which is contracting this the Lorentz index of the massive spinor-helicity variable. We'll call this part as a stripped amplitude. So the full amplitude is expressed in terms of stripped amplitude times the massive spinor-helicity variable. So so now we'll try to construct a 3-particle amplitude when there are two massive particles with same mass and spin and one massless particle of helicity h. Suppose the particles with momenta p1, p2 are massive and massless particle with helicity h. the form of the amplitude will, the form of the stripped amplitude would be like this, where the SL2C indices are also symmetrized. It is natural to use the following objects to span the total 2s by 2s SL2C space. The objects are like lambda 3 alpha and epsilon alpha beta. There is no object with dotted index because we are choosing to express the full amplitude in terms of only lambda I alphas. So the requirement for this construction are the follows. So they should obey the little group scaling of the massless particle, and they should be symmetric in the alpha indices and the beta indices, and also must produce the familiar massless amplitude in the high energy that we saw earlier. So with this these three requirements in mind, let us consider now what happens if we have a scalar, massive particles are scalar. So in this case, the amplitude will take the following form. It will be just a number with some x is some factor which should have a little group weight -2, because it has to transform as e to the power -2 when the 2h when the due to the little scaling of the massless leg. And this also the x factor should also has the mass dimension 0, because in 4 dimension the 3-point amplitude has mass dimension 1, and I already introduced a mass here. So the g mass dimension for g is 0. So to find this x factor, we can look at the 3-particle kinematics. So this tells us that this spinor product. Yeah. Is there any question? Okay, I guess no. So this spinor product must be 0. So this can be interpreted as this lambda 3 is proportional to this object. So we'll call the proportionality of this object as x factor. So x factor can be expressed like this, where xi is some reference. From this expression, you can see that the x factor has a little group weight -2 and mass dimension 0. So this is an appropriate candidate for this amplitude. Okay, so what happens to when the massive particles have a spin s? So in that case, we'll consider only minimal interaction. In that case, the amplitude takes this form, where we have the usual GMX form, and because these indices have to be symmetrized, we have this expression. So so here helicity is 1 and -1. So from the structure of the stripped amplitude like this, we can construct the full amplitude by multiplying the massive spinor-helicity variables, and the result is these. So for plus h helicity, the amplitude will take the form like this, and the minus helicity, it will be expressed in terms of square. So the bold-faced notations are indicated here like this. So they are just symmetric product of the spinor products of the usual spinor products. So although we need the x factor to express the 3-point amplitude, this factor will not appear in any higher point amplitude for local theory with minimal factor. We'll see an example of this. So before computing the massive amplitude, let me give you the proposal of our work. So the little group covariant massive massless shift is like this. Suppose we deform EI massive particle with momentum P and massless particle with momentum Pj, which have positive helicity, and deformed like this. Then one can show that the spinor-helicity variables associated to these particles can be deformed like this, where the shift vector is expressed in this form. So this is little group covariant because the shift in the spinor-helicity, the massive spinor-helicity variable retains the little group coherence in this way of deforming. So we'll denote such shift as ij of the type m plus. M is a m denotes the massive spinor-helicity variable, which is deformed in the square bracket, and the massless spinor-helicity is deformed in the angle bracket, which has helicity plus. So let me give you an example of 4-particle amplitude. So consider a scattering amplitude involving two massive spin-1 and two opposite helicity bosons. With shift of momenta P1, P2, there is only a single color order diagram again. So there's another diagram, but in that diagram, the two deformed momenta are attached to the same matrix. So we will not consider that diagram. The massive massless shift we are taking is 1, 2. In unitarity method, we need to consider another diagram which is attached, as I said. Okay, so using the recursion relation for 4-particle amplitude, one can write the amplitude in terms of this 3-point amplitude like this. And so we already have the expressions for these 3-particle amplitudes. Using that, one can see that the 4-particle amplitude can be expressed like this. We have to evaluate this the shifted spinor products at z equal to Zi. So how to do that? So first we have to find the Zi by using the on-cell condition of the propagator. So Zi will be like this. Using that and the shift of the massive spinor variables using this expression, one can evaluate these two spinor products. So using those expressions, one can finally arrive at the amplitude like this. So you see, this amplitude is symmetric in the little group indices of massive external particles 1 and 4 because of the square. And it also has a correct little group scaling for the massless particles as well. So again, this result can be verified with the amplitude computed by using the unitarity method, which is done in this paper. So this is an M plus type of BCFW shift. The other type of valid shift is minus M. One can also compute 5-point amplitude using the same shift using relatively less number of diagrams. Hence, we suspect that there is a valid shift involving the massive particle, one massive and one massless particle. So, is there any question up to this? Okay, so let me move on.
I can ask a small clarification. So when you draw the diagram for the 4-point, this one. So there, in general, you could have a massive 3-point vertex and a massive massless 3-point vertex also, right? So there could be a massive propagator.
Right.
So what happens?
Yes. Oh, so I forgot to mention. So if you allow a massive propagator, so what happens that in the right amplitude, you have a massive particle decays into two massless helicity massless particles, right? A massive spin-1 decaying into two massless particles with helicity plus minus 1.
Yes.
But that is not allowed.
Just kinematically, you are saying it is ruled out.
Yes.
Okay, thank you.
Okay, so now I'll review the proof of the valid BCFW shifts for gluon amplitude. The proof is a bit technical, so I'll first give the result. The valid BCFW shifts, as I mentioned earlier, for the computation of gluon amplitude are these three. Here, plus minus are associated with the helicity of the shifted external gluons. The only invalid shift is plus minus. So to set up the proof, we consider only a 2-point amplitude with momentum of the external states being infinitely large. The 3-point amplitude, which is the building block of any n-point amplitude, can be therefore constructed by just attaching the undeformed momenta to its amplitude. So we'll focus only on the 2-point amplitude. So if the 2-point amplitude itself is vanishing at large Z, then for any endpoint amplitude, it will also vanish at large Z. So the interpretation of this large Z limit is the following. So at large Z, both the deformed momenta can be thought of as like they going to be order Z. And here, if the momenta Q is real, then this scattering would be exactly like an iconal scattering. But in the BCFW case, Q is complex due to because the Q has to obey those conditions that I talked about in the early slides. But we can still use the idea of iconal limit by interpreting that in the larger momenta approximate a highly boosted particle, and the remaining particles which are not shifted at all collectively form a soft vector. So the scattering of the boosted gluon will then be understood by studying the quadratic fluctuation about this background. So we'll have to analyze this following 2-point amplitude. So 2-point amplitude is constructed by contracting the usual field theoretic amplitude with the on-cell polarization vectors for the massless particles. So the polarization vectors for the massless particles are like this. Here, xi and etas are reference spinors.
So, sorry, Arka, just a small clarification. So when you say 2-point amplitude, you mean in a non-trivial background?
Yeah, non-trivial background, right. So the background is this soft background,
okay,
which the particles are. So, to do this, we'll expand the gauge field in the Young-Mills Lagrangian like this. So A0 is a background field, and small a is a fluctuation about that background. We'll expand that, and to analyze this 2-point amplitude mu, we'll keep terms quadratic in the boosted field M. So after using the gauge fixing condition, dA dot A equal to 0, we get the relevant terms like this, where dA is the A0 covariant derivative. Now you'll see that at large Z, the first term will dominate because the derivative acts on the boosted field, but the second term is not will not dominate. But though the first term is dominating, we'll see the first term has also enjoys a special symmetry, which we call a Spin-Lorentz symmetry. But this symmetry acts only on the boosted field at large Z. So the usual space-time Lorentz symmetry is not there because of the introduction of this A0, but the first term has a emergent symmetry which we call Spin-Lorentz symmetry, acts only on the boosted field. So to manifest this symmetry, all the space-time indices can be trivially relabeled to the Spin-Lorentz symmetry basis like this. So alpha beta is the indices in the Spin-Lorentz symmetry. And the second term, which breaks this symmetry, is this. So this enhanced symmetry can be thought of as an emergence of Lorentz symmetry at large Z acting on the boosted fields. Here the space-time symmetry is broken by the background. So the first term in the Lagrangian contributes to all ordered Z terms proportional to eta alpha beta. Intuitively, this can be thought of as the conservation of highly boosted helicity of the highly boosted gluon. By utilizing this symmetry, that dominates at large Z, one can infer the following structure for this A alpha beta. So A alpha beta has these three parts, where all the ordered Z terms will be proportional to eta alpha beta, and so in the Lagrangian, the second term which breaks the Spin-Lorentz symmetry, it is proportional to this field strength, which is antisymmetric in alpha beta. So for this term, the contribution in A alpha beta will be like this, M alpha beta, but which has to be symmetric, antisymmetric in alpha beta. And any further insertion of these for these two terms will result in the terms where we have additional 1 over z subtractions. But those terms will be multiplied and are general matrix like B alpha beta. Okay. So the M alpha beta is antisymmetric because it comes from exactly one insertion of the second term vertex, and any further insertion will give you higher powers in 1 over. So though the terms multiplying this eta alpha beta diverges at large z, we'll see that when we contract with the external deformed polarization vectors, the full amplitude will vanish for these terms. So to see that, let's consider the shift of the spinor-helicity variables. So let's consider the shift ij, where I and j spinor-helicity variables are deformed like this. Now we'll use the word identity for the massless particles. The word identity tells us that A alpha beta contracted with external deformed momenta and the polarization vector must be 0. So here then we'll use the expression for the deformed momenta in terms of undeformed momenta Pj and Q to write to get the condition like this. So here all the deformed massless polarization vectors can be expressed in terms of external momenta and shift momenta Q like this. So using these expressions, suppose we consider the on-cell amplitude where the external states are positive helicity gluons, then we have to compute an expression like this. So from this expression, we can, so for this plus E alpha plus I has this, we'll use this expression, and for for jth particle, the positive helicity polarization can be replaced with this expression. But if you replace with this expression here, then we'll use this condition to write 1 over z times Pj contracted with A alpha beta, and then one can show that that will lead to the first term where eta alpha beta contracted with Pj alpha and Pj beta. But those P's are undeformed one, so that will vanish on cell. Similarly, the other helicity amplitude for other helicity configurations will also vanish at large z. But the amplitude where the external states has the helicity configuration plus minus, the amplitude grows at order ZQ, which is of course not vanishing at large z. So hence, the BCFW shift plus minus is not a valid shift for the computation of the. Is there any question? Hello? Hello? Can you hear me, guys?
Yeah, we can hear you. We can.
Yes.
Okay. Okay, so if there is no question, then let me move on to the proof of valid massive massless shift in Higgs shear theory. For this type of shift, one massive spin-on particle and one gluon momenta get complexified. So there are two valid massive massless shift of the type m plus and minus m. For example, if we complexify massive particle with momentum pi and massless particle with momentum pj with positive helicity, the valid shift will be like this. So the invalid shifts are m minus and plus m. So in particular, if you look closely at these shifts, the massless limit of these shifts, or the valid shifts, will lead to the valid BCFW shifts that we talked about. These plus minus, minus plus, minus minus, and plus plus. But if you look at the invalid massive massless shift, this will, so one in the high energy limit, one of the particular helicity configuration will lead to invalid BCFW. So without any proof, one can guess what kind of massive massless shift may be valid in the case of Higgs theorem. So that being said, let me now give you the proof. But before going to the proof, because it is a bit technical, let me give you the summary of the whole. So in this case, the soft background is in fact replaced by a static background of a collection of massive and soft massless particles. The resulting outgoing states are highly boosted massive spin-1 boson and a highly boosted gluon. At large jet, the dominant contribution to amplitude again comes from the helicity conserving term. So just like massless theories, the 2-point amplitude gets constrained by the Spin-Lorentz symmetry. Then we will use the word identity for massless gluons to constrain the subreading behavior. So the process that we will be considering is again a highly boosted gluon scattered through a static background, producing a boosted massive spin-on particle in the out state or vice versa. For massive massless shift, we will consider the following 2-point amplitude involving massive and massless particles with momentum pi and pj respectively. So the deformed 2-point amplitude, where the massless particles suppose have a plus helicity, will take the following form. So here we have replaced the polarization vector for positive helicity gluon with this expression. So there is a kappa, q mu, contracted a mu, and e hat. So E hat nu is actually the polarization tensor for the massive particle, but the massive particle has 3 modes. So it has this massive spin-1, this polarization tensor has 2 transverse modes and 1 longitudinal mode. So we'll show that for each mode, the amplitude vanishes at large. So the definition of the polarization tensor for massive vector boson is like this. It is symmetric in IJ. The theory we'll consider is the following. So we'll consider a SU2 gauge field and an abelian gauge field with the scalar coupled to the gauge field in this way. There are other terms like the potential of the for the scalar field, which is stabilize the vacuum around which we will do the Higgsing, but I will not indicate those terms as those are not relevant for our purpose. So following the analysis for Yang-Mills theory, we will do background expansion for each gauge field, and for massive massless shift, we will keep terms with product of massive and massless fluctuation fields after doing Higgsing. So I will not give you all the calculations to bother you, but I'll just simply write the structure of A alpha beta from those terms. The Spin-Lorentz symmetry constrains the structure of A alpha beta in this way. So you see there is no term which is helicity preserving because we are considering a massive massless shift. But if you, so in the case of massless shift within this theory, there is a helicity preserving term which is proportional to eta alpha beta. But in this case, that term is not present. So otherwise, the term M alpha beta is again antisymmetric and B alpha beta is a general matrix. For the transverse mode, the on-cell amplitude are treated as a massless amplitude at large Z, and then we can use the word identity for Yang-Mills theory and the structure of A alpha beta, this, and the polarization vectors expressed in terms of external momenta, like these expressions. We can show that the transverse mode vanishes at large. Okay. So for the longitudinal mode, the word identity for spontaneously broken gauge theory relates the longitudinal mode of vector boson amplitude to the Goldstone boson amplitude to the leading order in Z. So the longitudinal mode of amplitude at large Z can be treated as amplitude involving massless scalars and gluons. So due to this prescription, we will consider the following process for the longitudinal mode. So let me consider a 4-point amplitude where massless gluons are scattered with massless scalars, and the BCFW shift we are taking on these 2 legs. So for this process, the relevant Yang-Mills, we consider the theory, scalar Yang-Mills theory. The 3-point interaction that we need are these. So there exists at most order Z vertex due to the presence of single derivative acting on these scalar and gauge fields. So adopting similar background field method and choosing the Lorentz gauge condition, one can show that all the order Z vertices can be made order 1, but due to the order 1 over Z behavior of the propagator, the amplitude constructed via gluing of 2 sub-amplitude vanishes at large Z. So, and all the higher point amplitude also with scalar glue on shift will all be suppressed by additional 1 over Z factors due to the propagators. So, any endpoint amplitude will also vanish at large. So far we have shown that the transverse modes and the longitudinal mode of the 2-point amplitude, this amplitude is vanishing at large. So the massive massless shift that we are considering is a valid BCFW, a valid shift for computing known amplitudes. Okay. So the outlook of this talk is that we have derived a generalized BCFW recursion relation which includes a complex momentum shift of massive particle by making use of the recently proposed spinor-helicity formalism for massive particles. We proved the validity of the recursion relation for Higgsed Yang-Mills theories by extending the background field method introduced by Arkani-Hamed. In the spirit of the massive massless shift, it would be worthwhile to find shift involving 2 massive momenta relevant for the computation of all massive amplitudes. In this work, we use the new recursion relation to compute certain 3-level amplitudes. So one future goal would be to compute the loop amplitude using the new recursion relation. Yeah, so this is the end of my talk. If there is any question that I can take.
Let's all unmute ourselves and thank Arkajyoti for this wonderful talk. Questions? I have a question about if you go to the previous slide, so not the one after that, where you showed this gauge A dot del dot A equal to 0, this Lorentz gauge.
Oh, yeah.
So Lorentz gauge, but there is still this residual gauge symmetry that you need to fix. So this spinor-helicity, I mean, how do you fix that part?
Oh, yes, there is a residual gauge there, but so you can fix, but we don't need to fix in this purpose, because with only this gauge condition, you can see that all the order Z vertex can be made order 1. So that is our. I mean, I am saying that there is residual gauge, but we don't necessarily need to fix that also for this purpose.
Okay.
I have maybe a naive question. In your last slide, you said something about loop amplitudes. So, so yeah, can you just say what do you mean by this? Like, is it like you want to like have like contact terms giving rise to one loop amplitude of 4 scattering external scattering states?
No, I mean, so what we have in our mind that there are some processes which involves a loops, right? I mean, some amplitude. Suppose we want to compute so far for the 3-level amplitudes, those corresponds to the minimal coupling. But if you go to the loops, then you have corrections. So, for example, you have this magnetic dipole moment and stuff. So, for them, you have to compute the loop diagrams. So, for those, the results are there already by using the unitarity method. So, in our mind, we thought that maybe we can reproduce those results by using the loop and see whether this new recursion is efficient way to compute this, like in the massless case.
Any other questions? If not, let's thank the speaker once again for this wonderful talk.
Hey, thank you, Arkajyoti.
Hi,